Yeah, so today I'm going to show some preliminary results about our recent analysis of deep impact data to understand the speciation of lunar surface water. I also want to acknowledge that this part of the work is supported by the Clever team led by Tom Orlando at Georgia Tech. Let me see. Yeah. So as we know, knowing the speciation of the hydration on the lunar surface is very important for understanding its formation processes and also processes about destruction and cycling. And currently the speciation like either OH or H2O of lunar surface water is not well constrained. And we have both orbital and retained sample analysis showing there could be like a coexistence of OH and H2O on the lunar surface. And on the left plot, I'm showing a plot from Casey's paper back to a few years ago. This is a Sophia observation. The black dots are the H2O, while the red dots are OH plus H2O from MCube. On the red plot, I'm showing recent results from channel 5 sample analysis. This is you can see this impact glass speeds. They also found both OH and H2O in the sample. And as we know, in spectroscopy, the OH fundamental stretching overlaps with the overtone of H2O both near 3 micron. And in theory, the individual peaks can be deconvolved. So this in the table, I summarize the assignment of the band center to the speciation, like either OH or H2O. This is based on lab study and theoretical studies. And I want to point to you is the band near 2.92. This is assigned to H2O. And on the red plot, I'm showing a basaltic glass, the spectrometer in lab, and then we develop a model, try to deconvolve the individual peak. And the blue dotted line, I want to point to the blue dotted line. This is the one near 2.92. This is assigned to H2O. And we know there's molecular water in this sample. This is around 100 ppm. You can see the peak is showing very nicely there. And based on this model, we have two objectives. The first one, we want to determine the detection limit of H2O through deconvolving the absorptions near 3 micron. So particularly, we will assess the amplitude, the strength of the absorption peak near 2.92 that are assigned to H2O. And then we will apply this model to the deep impact flyby data of the moon to search for molecular water like H2O. So for data, and we have two different suites of data, and we will use basaltic glass and pure andesite samples with a known OH and H2O. This is measured in lab. And in orbital data, we're going to use the DI data. This is from Chris' work. And we only apply like a further photometry correction to account for the multiple scattering effects at a very high like angles. This is one example I'm showing here is a DOI 352 overlaying on the AURAC WAC data. You can see this is from this covers a very wide range. And some of the observations are in extreme case, like very high incidence or imminence angle. So we just apply like further photometry. On the left plot, I'm showing the lab suite of lab data. This is basaltic glass, the reflective spectra from like 2.5 to like around 7 micron. And you can see the 3 micron region. This is both OH and H2O show up here. And at 6 micron, this is very unique to H2. I think we heard this story a lot in the previous talks. And also, when we measured it there, like a OH, H2O, total water, and H2O in lab independently. Okay, so here's some results. On the left, on the right, you see one example. This is also basaltic glass. This is the reflective spectra near 3 micron after continuum removal. And these individual dashed dot lines are the deconvolved Gaussian peaks. And this sample, we know they run 1,000 ppm water. I think this is mostly OH because we don't see any H2O feature. And you can see the deconvolved 2.92 peak. So this doesn't make sense, right? Because these are assigned to H2O, it should not show up. As we know, you know, when you fit a curve, more parameters can fit better. So that means you can do overfitting. You can see the fitted curve, you even cannot see it because it overlap with the measured ones. And then we perform an F test. This is on the bottom, on the right bottom. You can see after the F test, it turns out that this peak, the H2O peak, is unnecessary. Statistics is unnecessary to reproduce the measured reflection spectra. So we applied this F test further to determine whether the H2O peak is necessary to fit the measured spectra. And then we deconvolved each spectra of those samples we have in lab, and then plotted their H2O content with the Gaussian amplitude near the 292 micron. That's the assigned to H2O. That was shown on the left plot. You can see we have a suite of different kind of samples and also a wide range of H2O content. So the take-home message from this plot is the Gaussian peak near 2.92, the H2O peak need to be above 0.1 to be detected. And then the detection limit of H2O is around 100 ppm. So that's marked by the pink or red box here. So you can see once the water content, H2O content above around 100 ppm is converged nicely. This is a linear trend because this is log scale. And also there's no apparent particle size dependence because we use, like you can see, a wide range of particle size, all relevant to the lunar surface. And then we apply the model to the deep impact data. But before that, we want to understand whether deep impact data has a difference with M-cube, another orbital data set. The moon mineral mapper also can measure the total water. We found that the deep impact data measured similar amount of water, total water, near 3 micron as the M-cube data. You can see there are 3 different flybys. It shows very great agreement with the M-cube data, particularly above like 60 degree. But I want to point it out, there are many differences. First, M-cube data are closer to the noon and also from the global average. While the deep impact data is, because there are not many data, so I have to lose it to like 11 a.m. to 13 p.m. So this has a wider range of local time, and also it's from a very regional observations, but it's still showing great agreement. And also we assess the diurnal variation of the total water. And we also found that it agrees well with M-cube data. So the bottom black lines symbols are from M-cube observation at the same region repeatedly. The above red lines and symbols are from DI data. At a similar latitude zone, 60 to 75, you can see they parallel to each other. That means the gradient is the same. So water varies at a similar amount at per unit time. The difference in the background could be due to many issues. For example, the different maturity, you have different exposure time to trap the water in the impact glass. So that is stable. You can see even near the noon, they are different. And also, like I said, M-cube from the same observation, the location, while DI data is from different locations, but still you can see the diurnal trends are so similar to each other. And now let's look at some deconvolution data results. So this is one example from DI data. We assess the total water, OH plus H2O is around like 700 ppm, while it shows the deconvolved 2.92 peak, and also after F test, it's still showing there. It could be due to the presence of H2O, but we think based on the strength of this peak, we think the total amount of H2O could be less than 100 ppm. And then we put all the data together. So we don't see notable latitude dependence, but this is very limited data. You can see this is only from south latitude 50 to 65. There's a slight decrease you can see from 50 to 65. it's interesting if you recall in the first slide, I showed that Sophia data also showing like a slight decrease, but this is very weak, and also like a very limited data, and also very weak or no downward variation. This is on the red plot. You can see this is from morning, noon to afternoon. There is a slight decrease in the noontime, but again, the variation is too weak, so I'm not sure this is a real downward variation or no downward variation.
Shuai,
Okay,
minutes.
yes. Oh yeah, this is the last slides. Do I have time to go through or no?
30 seconds.
Oh, okay, great. Oh, good timing. Yeah, so we developed a model, a skewed Gaussian deconvolution model, and to estimate the molecular water content from the 3 micron absorptions, and it shows like around 100 ppm detection limit for silicon minerals and glass, and that can be applied to any like spectral observations in future that cover like 3 micron regions of the moon and other rocket bodies. And the water estimated from DI and M-cube agrees well, and also the downward variation from the two dataset agrees well. And this is not a very conclusive, so we think there's no latitude, almost no latitude or downward variation of H2 in the DI data, but this is limited to spatial resolution and coverage of DI data, so need more observations. That's it. Thank you very much.